Yeah, I got interested in this topic through a postdoc of mine, Takashi Hosokawa. And when he returned to Japan, he had a series of students that began working on this topic. And it was based on a stellar evolution code and a radiation hydrodynamic code that I gave to Takahashi. So first of all, why are, let me tell you exactly the order of the talk today. I'll give an introduction and talk about cosmology simulations, because the first stars actually formed at a time when cosmology was important. Talk about the formation of stars, how stars can form with zero metallicity, and then talk about 2 and 3D collapse calculations combined with stellar evolution calculations. So the first thing point I want to talk about is why do we really care about these first stars? These first stars actually initiated the UV radiation that reionized the universe. It turns out that it didn't last very long. It was a short phase, but nevertheless, then subsequent generations of star formation could reionize the universe. They also produced the very first supernova and dispersed the first metal. So the metallicity of the next generation of stars is very dependent on the type of supernova of this first generation. Then there's a question about where did the supermassive black holes come from? We're talking about billion solar mass black holes in the center of galaxies. And finally, obviously, the subsequent formation of galaxies and their early evolution was probably strongly influenced by what happened in these first stages. So let me address the supermassive black hole question. And this does not mean 1/2. This means slide 1 of 2. I used this slide in an earlier talk, and they wanted to know, what does 1/2 mean? This is observations at z equals redshift z equals 6, cosmological redshift z equals 6, which is about 900 million years after the universe formed. Black holes of 1 billion solar masses have been observed. Now, if you say that this black hole came from a lower mass black hole and it accreted gas to get up to that mass, there's a limit how much mass a black hole can accrete. If you consider the fact that the black hole has a luminosity because of this material that's falling into the black hole, and the efficiency of conversion of mc squared is about 20%, this luminosity and the radiation pressure, the radiation acceleration of this luminosity can prevent material from accreting. So the so-called Eddington accretion rate depends on, first of all, this efficiency factor, the opacity of the material that it's accreting, the speed of light. This is the gravitational constant. And, of course, it's proportional to the mass. So this is a exponential growth of the black hole. And we know what the opacity is. We just look at electron scattering. And so the red line is the expected growth rate of a black hole starting from t equals 0 up to this billion solar masses. It's just a straight line in a log-log plot. And so the epoch of star formation, which is redshifts of 30 to a few 10, 12, this epoch of star formation, you seem to at least to have a seed black hole mass of 10 to the 4 or higher solar masses in order to get to this, accreting at the maximum rate. Now, of course, there's caveats to this discussion. People have tried to say, okay, maybe we have something called super Eddington accretion, and there's ways to get around that. And maybe your eta factor is 0.2. This 0, yes?
The stuff that is accreting.
That doesn't matter. At any point, it's ionized, and so you have to accrete against this radiation pressure at the same time. Obviously, if you accrete into a disk, it can get in closer to the black hole because it'll be something called the flashlight effect. But this would be one of these super Eddington accretion. But yes, definitely at some point, it has to accrete onto the black hole, get within a Schwarzschild radius, and it has to fight this radiation pressure.
I'm just wondering where in the history of the universe forming has.
Okay, that comes later. that comes later. This is just setting the stage of why we want to think about these first stars, because the first stars presumably either produced these first black holes or they were primordial. And the model of primordial black holes has they've tested some of the consequences, and that's less likely. So. Nowadays, people with the cold, dark matter, lambda CMD universe, it's from the bottom up. And I'll get to that also in my talk. So you first form the smaller objects, and they coagulate and form larger objects, and so on. That's I think is the standard theory now that we have WMAP and Planck observations of what the universe presumably looked like right at the recombination phase. And so exactly that point of how do you get this initial black hole? One of the models, and there's several models in existence. One of course being that you have lower mass black holes that somehow coagulate. But one of the models is this so-called direct collapse model. And you first have to produce a supermassive star of about 10 to the 5 solar masses. And that type of star would collapse directly into a 10 to the 5 solar mass black hole. And so we've only redirected the question, how do you produce a supermassive star in this scenario? So we want to know how massive were the first stars in the universe. And this is slide 1 of 2. And for many years, the standard answer was, well, there were several hundreds of solar masses. And these were based on cosmological simulations. Tom Abel, other folks did this. And it's summarized in this review article by Brom and Larson in Annual Review. And the reason this is important to know, the mass of these first stars, was the fact that if you have stars less massive than 100, say in the 2 to 80 solar mass range, they would produce core collapse supernova. These are sort of regular supernova. You would have regular element abundances in the material that's spewed out into the local medium, and then from which the next generation of stars would form. If they are a pair instability supernova, a so-called pair instability supernova, these would explode but not produce a compact remnant. It completely disrupts the star, and it would produce an entirely different elements abundance pattern. And the really massive stars, more massive than, say, 250 solar masses, they would collapse directly into a black hole. There wouldn't be an explosion. There would be no enhancement of the metallicity of the surroundings. And in between these two, there's another type of so-called pulsational pair instability supernova. And that's, you get the pair instability in the center, but they pulsate and they expel material down, and they end up to be an 80 solar mass star that then collapses.
Why is it that the most massive ones overcome the pair instability?
It's the pair instability sucks up energy, and so that causes the thing first to collapse. I'm not going to defend supernova calculations, but you know probably that all the supernova calculations that people do in 3D, they have difficulty getting the things to explode. And so these are calculations, the pair instability supernova are calculations where they they get to a certain density, and then the parent stability at some point works in the other direction. In other words, you win energy, and that's what disrupts the entire star. For the more massive ones, they don't get that bounce, and please don't ask me to explain why. It may have something to do with neutrino transport. In the one case, they're able to stop that collapse. In the other case, they aren't when they get to be too massive. And but this is the standard quote knowledge as far as supernova goes, and I'm going to stick with it. So there have been a number of recent papers that they challenge this paradigm of the 100 solar mass and greater population 3 star. And a number of authors have pointed out that fragmentation could produce multiple protostars. There's an analogy in our own galaxy in population 1 stars. The trapezium cluster is not 4 stars, but actually 14, because each one of the trapezium stars is a multiple system, and there's a high rate of spectroscopic binaries among massive stars. So, so fragmentation indeed could play a role and produce multiple stars of lower mass. But the other point that the earlier calculations did not take into account was UV feedback. And UV feedback means that when your massive star forms, of course, it's very hot, and it starts ionizing its surroundings. And when it ionizes its surroundings, you have, first of all, higher pressure, but you also have electron scattering, which the radiation can help blow the material away. And it turns out that UV can limit the growth of these population 3 stars. And this was one of the first projects that my postdoc and I worked on in several years ago, 5 years ago. So I'm going to first describe in words how these stars form. And there's actually quite a good analogy with star formation in the present day, except for the first couple of bullet points. So in this cosmological model, the first thing you form are these mini halos of dark gas. And there are 10 to the 5, 10 to the 6 solar masses. And within these mini halos of dark matter, then your baryon matter can flow into the potential well created by these mini halos. And as long as that gas is able to cool, and you do have a little bit of molecular hydrogen and molecular HD, as long as you're able to cool, this compression of gas doesn't produce a corresponding increase in the gas pressure. So eventually it becomes gravitationally unstable, it begins to collapse, and the densest regions do become optically thick because the cooling is in individual cooling lines of hydrogen. These are mostly the rotational lines of the molecular hydrogen and HD. And when they become optically thick, then any further compression causes an increase in pressure, and so you end up with a quasi-hydrostatic object of a few Jupiter masses at the very center, and then material still continues to rain down on it. If the material has low angular momentum, it goes directly onto the star. If it has too much angular momentum, it cannot go directly on the star. It first goes into an accretion disk, and the further accretion on the protostar depends on angular momentum transport. Now, in this early phases, you have basically 0 electrons. So magnetic fields do not play a role in this as they would in present-day star formation. And the angular momentum transport mechanism for these types of stars is the fact that the disk that you form fragments into clumps. It becomes very clumpy. It forms spiral density waves, and your angular momentum transport is done by tidal effects in that disk.
Electrons, just because it's all hydrogen?
Yes. It's all hydrogen, and at high density, any few electrons that are left over, they recombine So it's just too few hydrogen. In their quasi-static object itself, it can heat up and eventually produce those electrons, and that's when H minus plays a role, but that only plays a role for the protostar itself. And because it's fully convective and differentially rotating, you probably have a dynamo mechanism. And so your protostar itself could have magnetic fields, but it doesn't influence the material falling onto it. So while it's accreting material, this object is also contracting towards the zero-age main sequence on a Kelvin-Helmholtz timescale. So what did we do? We did a multi-step process, starting with a cosmological simulation, 3 megaparsecs large. And remember, we have to eventually get down to fractions of a solar radius. So I have to somehow overcome many, many orders of magnitude of space. So we first did a cosmological simulation of dark matter, a mixture of dark matter and gas, starting from z equals, that's a redshift of 99 and calculated up to a redshift of 9. That's at a universe age of 17 million years to 551 million years. We used an SPH code called Gadget2 and include the chemistry, because the chemistry is very important for producing your coolant, your H2 molecules and your HD, while it's collapsing. That was our first step. And that we come up with this background of, this is now the dark matter density is here in the background. The next step is we looked at, there's certain areas of interest. We looked at, or picked out 55 areas of interest. And we redid the calculations, starting from 99. But for these calculations, we use the results of this coarse calculation with 500 million particles. We use that as a boundary condition to show how much material is flowing into this area of interest. And we do 55 simulations from z equals 99 to z equals 9 with this new code where we focus in on a particular zone. So that was our step 2. At some point, we see that the gas begins to collect in these mini halos that we're forming. And we end up with a total of 1,540 gas clouds. And we calculate that up to the point that the first clouds look like they're gravitationally collapsing. So this is our distribution now as a function of redshift, the distribution of dark matter halos, and it's color-coded according to mass. That's to the left. And to the right, we have the same information. Now it's as a function of mass, we show the distribution. And the color codes are the various redshifts, cosmological redshifts, or ages. So this is our starting model for the 1,640 gas clouds. So the third step is we now zoom in on each of the 1,540 gas clouds and put all of our computing power, SPH power, into following the evolution of these gas clouds, each one of them as a collapse. And we can, with particles splitting in SPH, we can get to higher and higher resolution. And we always ensure that a gene's length is being sufficiently resolved. So we call this a grandchild SPH simulation. The Papa simulation is the big one. And then we have the zoom in daughter simulations. And this is the grandchild simulation. And then we continue them until we get a central density of 10 to the 7. So now we know what time each of these gas clouds reaches this 10 to the 7 particles per cubic centimeter. And we have a redshift-oriented list. Now comes the real hand waving. We followed representative, ideally you would want to take each of these 1,640 gas clouds, or 1,540 gas clouds, and do 3D simulations. But we at the time had a 2D code, which is a radiation hydrodynamic code coupled with stellar evolution. We first of all, in each of these gas clouds, figure out where's the center of mass, then what is the total angular momentum vector through the center of mass, and we azimuthally average the density around this total angular momentum vector to produce an actually symmetric starting model. Then we use a so-called nested grid hydrodynamic code, which is able to get high resolution down to about an AU in the very central zone. And we followed this with the time-dependent chemistry and with FUV and EUV transport. That's UV photons that can dissociate hydrogen, and the EUV are UV photons that can ionize hydrogen. And we calculated then the collapse of each of these clouds and followed the also the evolution of the star at the same time, figuring out when is the star going to become hot and actually produce the UV that would stop the further collapse. From our about 130 simulations that we did with this code, we derived then a fitting formula for figuring out the final mass of the star as a function of the cloud properties and external UV field. So let me go through that. This is an example of one of these collapses. So while the protostar is accreting material at a high rate, it has a tendency to bloat up to a large radius. And it's cool because it's a large radius. And after it reaches this maximum of about 1 AU, that's 200 solar radii, and 6 solar masses, the protostar slowly contracts towards the main sequence. At 20 solar masses, the radius is decreased to about 10 solar radii, and the effective temperature is about 35,000, and an H2 region begins to develop. And this is this first picture. I'm showing temperature on the left, density on the right. The scale of this is about 3,000 AU. So we're just looking at the central zone. The typical temperature here is about 300. The typical densities, this is the log density. Of course, it's very strongly density peak. And there's something that you can't see in this plot, but there's a central disk. And so this is when this star first turns on and begins to ionize the material outside. The ionization front, or the H2 region, expands in the direction it can expand most easily in, perpendicular to your disk. And this is the axis of rotation, so it goes along the axis of rotation. And eventually, this H2 region dispels the cloud. And you end up with in this case, a 42 solar mass star. And so this is much less than the massive gas that was in here. It could have produced a 300 solar mass object. So we then did a study of what happens when your cloud is illuminated from the outside with UV. And this is important because these UV photons would destroy your coolants. And because it can't cool effectively, it turns out you get much higher masses. So this is the exact same case calculated by changing the amount of UV irradiation, the dissociating radiation in units of 10 to the 21 ergs per second per hertz per steradian. And the case in black here is with 0 external radiation. If you have in units of 10 to the 21 ergs per second per steradian per hertz, if you have a tenth of those units, it hardly changes the evolution at all. This is the accretion rate as a function of accreted mass. So this is also something like a time. And you can see that the final masses in these two cases are 50 solar masses and 61 solar masses. So this happens with no irradiation or very little radiation. But as soon as you have higher irradiation, your masses become a lot larger. So it's the same initial conditions. You're irradiating it from the outside, and you end up with an 883 solar mass object.
what is the physical mechanism that when you add the radiation that you actually can accrete more?
It sounds counterintuitive. Because you're destroying the cooling, you're delaying the formation of your protostar. So the cloud is able to, it collapses slower. And because you delay the formation of the protostar, when you finally do form the protostar, this material then rains down. You have a high accretion rate, and the high accretion rate is maintained for a longer period of time. And because you can maintain this high accretion rate, the protostar is bloated, and it stays bloated. And you can't overdo it, though, because just going from 1 to 10, you've already decreased it by 40%. So this is the most massive one we got in the simulation, and then we increased it even higher, and then exactly that happens, and it's really unable to cool effectively, and you get lower masses. So we have these simulations. Yes, yeah.
Can you get like Rayleigh-Taylor instabilities or 3D type instabilities that can
we can't in the 2D, or it doesn't look like it in the 2D. After I get done with the 2D, I'm going to talk about the 3D. So yeah, and if I don't answer your question, remind me, please. So this low UV illumination produces what we call population 3.1, primary population 3 stars. Once you get higher UV illumination, then you produce something we call population 3.2D, D for dissociation. And there's also 2I for ionization, but I'm not going to get into them because there were very few of those. But I'm just going to consider these two types. So we have a redshift-oriented list of clouds. We have our fitting formula. So we start off with our very first star. We know that very first star, we know all the parameters we have of that cloud. We use the fitting formula to produce, and also it has no external irradiation. We calculate its formation, its mass. Once we know its mass, we know what its luminosity is. For its main sequence lifetime, we know its UV contribution for all subsequent generations of population 3 stars. And of course, that source of UV will die off both in time and in distance. So the subsequent formation of population 3 stars, we can figure out what is the illumination of these subsequent generations and figure out what their masses are and what their UV contributions are. And we just work through this redshift-oriented list of 1,540 clouds and come up with a initial mass function. So here I'm showing the UV intensity of J21. And so at Z equals 25, this is the first star started forming at around Z equals 30. But at Z equals 25, you have these pockets of a high UV intensity. They're forming then the population 3.2 sub D stars. And then between 20 and 19, 19.5, 19, this irradiation actually dies out. The universe is still expanding, right? And so the illumination is being diluted geometrically. So by Z equals 15, you have very little of the pop 3.2 Ds. And this is now our initial mass function calculated with this method. We formed one, I believe, 6 solar mass star, and we have a 1600 solar mass star, but generally have this shape. And there seems to be a reason that we have this double peak structure. If you look now at the redshift-oriented, when did these different types of stars form? And prior to Z equals 18, or actually Z equals 22, we didn't get any star that was less massive than 100 solar mass. So the initial stars that formed were 100 solar masses and higher. But as time goes on, redshifts gets lower, we start forming this second population of population 3 stars. So we now have our initial mass function, and we can figure out what type of supernova and supernova remnant we have. Rather than looking at a table, I want to show that in this diagram. So we have about 3% of the stars produce your regular core collapse supernova and a neutron star remnant. Another 6.8% produce these large mass black, this should be low mass black holes. And again, these are core collapse supernova. Here's your pulsational pair instability supernova, and that's about another 10%, and 25% lie in this. These are your pair instability supernova, and the high mass supernova are about 60%. So now, ideally, like I said, we would like to do 3D calculations, but they're very expensive. And we use this IMF using fitting formula derived from a 2D code. And the question is, how good was our 3D code? So we had to, we started with a new code. My code wasn't able to go into 3D very easily. So we started with the Pluto grid-based code in 3D in spherical coordinates, and we added all the bells and whistles that we had in the first code. And it turns out we could only consider 5 representative cases. And I'm showing on the background these cloud parameters, the various cloud parameters for the 1540 stars in Sion. These are the background. And these are our 5, quote, representative cases that we chose in this. This is the Jeans mass as a function of redshift. This is the angular momentum as a function of a redshift. And this is something called the infall rate at the Jeans radius as a function of redshift. And these are some other parameters. These were the parameters we used for our fitting formula in addition to the UV flux, the external UV flux. So the first thing that we found out when we did it in 3D was we didn't get our plane, our disk, to be in one plane. The material that's falling down onto the star has different angular momentum and also different orientation of the angular momentum vector. So we got these crazy disks that were flopping all around, but generally the H2 region, which is here in red, we're still in the, quote, polar direction of the main angular momentum vector. That was the first thing we found out, and I think that also has applicability for present-day star formation. People who do models of present-day star formation always start off with a more or less spherical and axial symmetric configuration, and they probably should consider a little bit more turbulent starting conditions. So the disks are flopping around, and these are the 4 representative cases. Each of them did produce an H2 region, and more or less in the along the poles of these things. And I'm showing again a temperature to the left and density to the right, and using these color codes. And this is a typical case D. We have the hydrogen dissociation front, and then here a small H2 region. And as time goes on, this H2 region expands in the more or less polar direction. And in this typical case, we ended up with a final mass of 67.4 solar masses. And in the 2D case, we had 55.5. So this was encouraging. However, okay, let me, again, before I go on, explain the importance of UV feedback. If we had no UV feedback, we turn off the UV feedback, the things continue to accrete material. If we have only dissociating feedback, but no ionization, we turn off ionization. We can produce really massive stars. But if we have both ionization and dissociation feedback, that's when we limit our final mass. I just wanted to point that out, that we do. In the 3D also, you limit the final mass because of the UV feedback. UV feedback from the central star itself. And we learned something else. The 3D simulations were a lot clumpier. You asked about Rayleigh-Taylor instabilities, and what happens is they become a lot clumpier, and the accretion, which is given here to the scale is given here to the right. The accretion is this thing here. It's a lot burstier is a good way to put it. And the way that the stellar radius reacts to this is that if your accretion rate goes above a certain critical value, which is about 5 × 10⁻²⁰ solar masses per year, your star bloats up. And if it drops below that, then your star can Kelvin-Helmholtz contract. And if the accretion rate goes up again, it bloats up again. And so this time here is mirrored in this diagram here showing the internal structure. But you see that we're going through multiple phases of the star bloating up. And because of this accretion burst and burstiness, our final mass was 600 solar masses in the 3D case, whereas it was below 300 in the 2D case. So this is a major difference from 3D. And we also did try to do the resolution, higher resolution. We get the same, at high resolution, we get the same general spiral density wave. This is within one of the disks. But at higher resolution, the disk becomes a lot more clumpier, and it becomes burstier, and we end up getting higher masses. This is just in case B for the first 1,000 years. We had, in the regular case, 33 solar masses. Here we have 45 solar masses. So what we've learned from this is that we haven't really resolved, we don't have a high enough resolution in 3D. So I'm running out of time now, so the question I wanted to ask at the beginning was, can we produce a 10 to the 5 solar mass star? And we did that. I'm going to jump through this by considering what happens if we could keep the accretion rate going for a longer period of time. And it turned out that this critical rate is 6 × 10⁻² solar masses per year. In that case, our star bloats up and stays bloated up, as long as we can keep the accretion at that high rate. If we go below that, we get some of these oscillations, and that the oscillations in radius and stellar radius would mean that the star eventually could produce UV photons. Observations? Well, we haven't seen a POP3 star yet. And ideally, a 0.9 solar mass POP3 star or lower mass should be observable. And observable by having zero metallicity. Pollution by interstellar dust would be negligible. We conclude from this that the lower mass cutoff of POP3 stars should be greater than 1. The other thing we want to look is abundance patterns of galactic metal poor stars. And there's a database called the SAGA database of metal compositions of all galactic metal poor stars. They have to be lower than 10⁻³ with respect to solar in order to get into the database. And you see they clump around this area here, which is what you would expect from core collapse supernova. The pair instability supernova, you would get an entirely different abundance pattern. And so apparently in the SAGA database, there's nothing that would look anything like a star that had been polluted by a pair instability supernova. There is, however, one star, Aoki et al. Found a chemical signature of one star that looked like it, and they conclude that this particular star formed out of from the material left over by a massive star which had 100 solar masses or more. So this would be the pair instability supernova. So conclusions: this bloating phenomena, accreting material onto a star at a rate that is sufficiently high that it cannot react thermally, causes the star to bloat. It goes all the way back to the Hayashi line. It becomes a red supergiant. And as long as you can keep this rate up high, they can remain bloated up at least to 100,000 solar masses. The radiation from such a bloated star in the metal-free material that's trying to accrete on it is transparent to the surrounding gas, or the surrounding gas is the other way around. The surrounding gas is transparent to this radiation because it's too cool. There's no UV feedback. Ultimately, if your accretion rate drops below this, then your star is allowed to contract, and UV radiation feedback inhibits the further growth. So I would conclude that supermassive stars could be formed in the early universe. And we've done simulations where we've done stochastic accretion. And you get by with a quiescent phase if it's less than 1,000 years old. And you'd have to then start accreting at a high rate again. The supermassive stars will presumably eventually collapse into a black hole of equal mass. However, no one has ever done this calculation. What do you do? These things probably have at least some angular momentum. So I think it'd be nice to know what happens when a star becomes actually unstable. This is a relativistic instability. They begin to collapse. What do they really do if you have a little bit of angular momentum? And our studies of the population 3 IMF, they may still have too many high mass stars to explain the abundance pattern in galactic stars. So we have some more work to do, I think. So our future outlook, 3D simulations, we need to increase the resolution. We need to verify the robustness of our previous results, or see how they were not robust. Like to consider forming multiple stars in that central sync cell of a AU or more. See what happens if instead of forming one star, you have multiple systems. I'd like to also find a stellar evolution code. If you know of any, let me know. That can take care of non-zero angular momentum and non-spherical accretion. In other words, the accretion is presumably through this disk. So it presumably gets to the equator of the star. I always assume that I have a spherically symmetric star and the accretion is everywhere. So what happens if the accretion is in the equator? So somehow this material has to be moved around the surface of the star. And of course, I'd like to see what happens when you form a black hole when when your star eventually collapses. Thank you. Yes.
Now you concentrated on sort of the way to end up with these supermassive black holes that presumably then are the seeds for the galaxy formation. But another aspect of all of this must be in just the nucleosynthesis,
Yes.
the underlying helium that we are working with
Okay.
now. So, would you comment on that?
Okay. The amount of material that participates in this first generation of star formation is actually only a small percentage of the baryonic material. Most of the baryonic material is still outside, waiting to do other things. So this is presumably a very local phenomenon, number one. I don't think helium is going to be enhanced at all, or certainly not measurably. So that really, it's only the later generations, the population 2 stars, that do the heavy lifting as far as the helium abundance is concerned. The thing is that these first stars will pollute the surrounding area, and they form then the next generation. You would probably the oldest pop 2 stars, which have been polluted with these metals. And to me, it's surprising that all of the really low metallicity stars that we can observe today, that are, the extreme pop 2 stars, that they all have abundance properties of a core collapse supernova. And I don't know if it's because, and the pair instability supernova, we have one example that is probably a pair instability supernova. Out of a database of several hundreds. So I don't know if it means that our IMF is wrong, which is highly likely, or are the supernova calculations wrong? Because, like I said, supernova calculations are very, very difficult to get them to explode. And I think that question is still unanswered. Yes?
So to accrete 10 to the 2 to 10 to the 5 solar masses, you have to get rid of a lot of angular momentum.
That's right.
And you said these disks aren't magnetized, so you don't have the MRI to help out. So
That's right.
How do you? Is that a substantial problem? Does line work?
Because we're doing 3D calculations, we can actually see the formation of clumps in the disk, and the clumps interact. There's a tidal dissipation that causes the angular momentum transport. We're now doing thin disk calculations at a much, much higher resolution of what's happening in the disk, and we're finding that some of the clumps actually get expelled, and that helps get rid of angular momentum. And the accretion is becoming, as we go to higher and higher resolution, even higher than what I talked about today. These are unpublished results. We're still working on the paper. The main mechanism of angular momentum transport is the tidal interaction of individual clumps. And the individual clumps flow into our central sync cell. And we assume that it eventually gets onto the star more or less immediately. That might not be true. We haven't really considered what happens right at the stellar surface or really close to the stellar surface when you get one of these clumps that come in. But it appears to be also a mechanism that can work for present-day star formation.
I mean, you have an Oort cloud of clumps around the system?
Yeah, mostly concentrated in the disk. Maybe I can have that here somewhere. Probably not. Oh, this is not. Oh, it's wrong screen. So let's see if I have. Oh, here it is. This is now the accretion, the clump spectrum that we're producing in the disk, and this is the accretion rate, which is extremely clumpy. Yeah, and this is what the disk now looks like as we go to even higher resolution. So that's doing your angular momentum transport. And these circled things are the clumps that have been expelled. So this is work in progress.
And this is done with SPH.
This is actually done with, let's see, this is done with SPH. No, excuse me. This is a grid code, and it's a grid code in 2D. So we're assuming a thin disk approximation. We have a certain Z assumption, and this is really the highest resolution we can go to at the moment in 2D. So, this I think is going to be something of the future. People who do star formation, even present-day star formation, are going to have to start thinking about this mechanism also. Clumpy accretion. So your stellar evolution. Let's put it this way: the Hayashi evolution, that you start somewhere on the Hayashi line and you move down and eventually go through a fully convective phase and then a radiate phase and then get on your zero-age main sequence. I think that entire paradigm is wrong. You're going to start off with something like a Jupiter or several Jupiter mass object, which accretes material, even in present-day star formation, accretes material at a very stochastic and clumpy rate. And that will affect how your pre-main sequence star looks because of this phenomena of bloating. Yes?
You mentioned the accretion mostly in the equatorial region.
Yes.
Now there's one question is, first of all, what is the significance of understanding better the nature of where exactly it accretes onto the star. Is that important? And secondly, magnetic fields would probably be playing a role in those stars already.
Yes, yes.
Polar areas. And also, of course, if you have a spreading layer that has been studied in white dwarfs and
Right. Yeah. So you're right. The stars themselves, I think, they'll be dynamos. People have demonstrated that pre-main sequence objects can produce dynamos, and so presumably these stars also are dynamos, have magnetic fields, and any ionized material, they can interact with ionized material. The problem is that at 300 Kelvin and zero metallicity, you don't have the alkali metals, you don't have the dust particles, so you don't have any ionization. So even though you have magnetic fields and you might be able to expel some of your material that you've accreted as long as it's ionized, but the disk itself is going to be completely neutral. So the surface of the star, obviously, you're going to have H minus and things like that. So my stellar evolution code is spherically symmetric, and so with a gray atmosphere, what happens is if your star becomes flattened, you have a high angular momentum star, and you're accreting in this belt, and that's mixing up. I have no idea how that's going to affect the evolution. When I say it's spread over the entire surface, the star bloats up. Does the same thing happen if you actually do a 2D or a 3D calculation of how that star accretes material? I don't know.
I mean, the star you would probably naively think should be fully convective, right?
Yes.
And maybe that exactly is not the case.
Yeah. If I can get back to my original, find it somewhere. I didn't show some of these, what I call Kippenhahn diagrams. So let me see. This is one. Yeah, these things, they're bloating up, even though they're not fully convective. White is radiative, and yellow is convective. So even the radiative zones are bloated up. And this is not in thermal equilibrium. It's in dynamical equilibrium, mechanical equilibrium, but they're not in thermal equilibrium. And of course, in the later phases, then you get this thing is fully convective, and you have a shell burning, a deuterium shell burning, because the material that you're accreting, it has some deuterium in it, and so on. So yeah, the stellar evolution is a little bit more complicated. It's not intuitive because we're not looking at stars that are in thermal equilibrium. Yep.
So in all of this, dark matter is only just present with its gravitation. Everything else is sort of conventional physics.
That's right. That's right. And when you're talking about these scales, the dark matter no longer is playing a role. It's playing a role on a larger scale to collect the gas. But once you start getting into the potential wells of the dark matter, mini halos, then the gradients of the potential are negligible. But we still have them in there. It's just a background potential that we put in there.
And so, and that all of this physics is going on with the dark matter just sort of sitting in the background, if you want, is the explanation why it took so long to realize it's there?
Yeah. I mean, dark matter only plays a role on larger scales. For our own galaxy, it's not until you get around the solar circle and outside that you start noting, wait a minute, there's the rotational velocity is too high. Yeah.
Hey, one more question. You mentioned James Webb Space Telescope
Ah.
on the last slide, and
Yeah.
I want to know whether there's some predictions you follow that you think James Webb will be able to address.
I'd love to be able to see a supermassive star of 100 solar masses. And James Webb will be able to see it. Not directly, but with gravitational lensing, you should be able to find areas where you can look back to z equals 30 and maybe find some of these really, really luminous, cool stars. When I say luminous, cool star, how luminous? We're talking about 10 to the 9, 10 to the 10 solar luminosities. The sizes are larger than the solar system. I mean, when I say bloated up, these stars are larger than the solar system, and they're really cool, featureless, red supergiants. And I don't know if there's anything higher you can say than the supergiant, but so yes, they should be observable. And obviously, you would also want to look at the metallicity of these first galaxies and the metallicity distribution of the first galaxies to see if you can find some sort of abundance gradient that might point to whether the pair instability supernova were at some point more, at a higher rate. In other words, maybe our population 2 stars, extremely old populations 2 stars are not representative of the metallicity in the early universe. And maybe you have to really go back in time and look at galaxies to see whether the IMF has really been skewed. Our problem is every time we try to lower the mass, we somehow seem to get higher masses for our first stars.
Okay, so let's bring our speaker again.